Good morning, good afternoon, and good evening. Thanks for joining us. Welcome to this intermediate and advanced breakout track on day two of Spring One. My name is Aditya Tripathi, and I'm the Spring Product Marketing Manager here at VMware. Today, in this track, we'll dive deep again into some of the most important topics for the Spring community right now. To kick things off this morning, we have Spring Native. As you're all aware, Spring Native was launched in beta in March this year, and the project has seen some fantastic growth and community support. We've got 2,000 plus stars on GitHub and more than 250 folks already. So thank you. Next up, we'll hear from Sébastien Deluise, who's a Spring Framework committer and a key member of the Spring Native team on what the team has been up to this year.
Thanks for the introduction, and hello, everybody. I'm Sébastien Deluise. I'm a Spring Framework committer. I have been involved in the web and reactive support. I have been introducing the Kotlin support in Spring applications, and I have created an experimental project, Spring Foo, which is basically about exploring how to build Spring application with functional constructs. And today I'm here to talk about Spring Native. Let me share the slides. Okay. So usual disclaimer, because what I'm going to present is work in progress, likely to change, and mainly shared for informational purposes. Feel free to join the discussion. Make sure you have already registered on spring1.io. Go to spring1.slack.com and join the session-spring-native channel. And at the end of the session, we will share a link to the Q&A session. Let's begin this presentation by a little flashback. In March, some members of the Spring team announced something special. It was done by myself, Andy Clement, who is a director at Spring and who is heavily involved in Spring Native technical aspects. Brian Clausel, Spring Boot and Spring Framework committer, Jen Schroeder from Spring Data, Ria Stein from Spring Security, and David Sayer, Spring Boot and Spring Cloud co-founder. What we announced in March was Spring Native Beta. That was a way for us to share that Spring Native and the native support for Spring Boot application has reached a certain level of maturity in terms of footprint, in terms of native compatibility. And it was also the opportunity to add Spring Native to start at spring.io to allow an easy start for Spring Boot native applications. And honestly, the feedback was huge. More than 50,000 views on YouTube, a lot of activity on Twitter and other social media. And we got plenty of feedback and pull requests of people, Spring developers contributing to the project. So thanks a lot for that. So let's talk about what is Spring Native. In summary, Spring Native provides beta support for compiling Spring Boot applications to native executable with GraalVM, providing a new way to deploy Spring Boot applications that then run extremely efficiently. So that's really about runtime efficiency. I'm not here to say that native fits every needs. GVM and native are complementary and offer different trade-offs. So while the GVM shines in terms of build time, maturity, and performances, native is hard to beat in terms of startup time and memory footprint. And it really depends on your context and your workload. For example, in terms of performances here, latency and throughput, if you have a cloud instance with a lot of CPU and memory, sure, GVM will be faster because it performs more runtime optimizations. But if you are running that on a very memory constrained machine with low CPU, native could be faster because it will give less memory and more power to your application in terms of heap memory, for example. So it really depends. Typical use cases I would like to share today are the following. The first one is sustainability, because native allow to run your Spring Boot applications with smaller and cheaper instances in the cloud. So it's good for the planet and it's also cheaper for you. So that's interesting. The second use case is Kubernetes. Native allow lighter pods. And in terms of scalability, for example, if you are using native applications with Knative, which allow to go scale to 0 and only start containers when you are receiving requests. I think the native characteristic like instant startup allow to scale up and scale down very fast and are a very good fit with Knative. The third use case is obviously serverless that require instant startups, so that's a no-brainer. And the last one is microservices, because when you are splitting your system into multiple microservices, With the GVM, you are going to pay a tax because basically each instance with the GVM infrastructure will consume quite a lot of memory. With native, the cost of splitting a system into multiple microservices will be less an issue. Our goal in summary is to allow Spring Boot developers to compile their Spring Boot applications to native executable with as few changes as possible. It will require some changes. So for example, updating your build or maybe upgrading your Spring Boot version. But we really target to allow you to benefit of native with the minimum modification in your applications. There are various challenges, and on GraalVM side, some GVM features are not supported on native. So for example, it's not possible to generate bytecode at runtime. There is no class lazy loading. Native is super efficient, low memory consumption, but every classes or resources are loaded at startup, while the GVM will lazy load the classes as they are used. That may change in the future, but for now, that's how native behaves. Another important point is that native executables compiled with GraalVM support reflection, proxies, resources, etc., but that need to be configured at build time because while the GVM is super dynamic and do a lot of things at runtime, on native, much more stuff need to be defined at build time. So that's a challenge. GVM libraries are mostly untested on native, so it's a challenge because each framework needs to provide the native support, do the testing part, and obviously it just integration testing level. It's less, it provides less quality than a proper native testing for each project. Compatibility versus footprint is a kind of eternal battle because native image is initially super efficient, but there is currently an effort to make it more compatible with the existing GVM to reduce the differences between the GVM and the native ecosystem and avoid to have two super different flavors of Java. And usually when you increase compatibility, that's impacting the footprint. So we try, the GraalVM team, ourselves and others to find the right trade-off between those two characteristics. And the last challenging point is long build time. You will see with concrete figures that native builds are much longer. On Spring side, runtime reflection used with the annotation-based programming model is a challenge because it's fully supported by GraalVM native, but it requires explicit configuration. So that's a challenge in terms of compatibility. And it's impacting the memory footprint because reflection on native is costly. So you may want to limit that. The second point is that Spring really care about API backward compatibility. So we want to support native without breaking our current contracts and programming model in order to allow you to not modify your application to go native. The last point is that all the work that we have done until now on Spring Native is based on Spring Boot 2 and Spring Framework 5. So no major architectural changes. So that was a challenge to do that without changing framework and boot. Let's now have a deeper look about how you could start your next Spring Boot native application. So your native journey starts on start.spring.io. I'm sure Josh will be happy about that. You go to this website, you can add the Spring Native dependency that is available in the regular field. And you notice that it's also available in popular IDEs, so IntelliJ IDE, like in this screenshot, Visual Studio Code, NetBeans, or Eclipse. One of the big added value of this start.spring.io integration is that the build will be configured automatically to support native application. That means that it's going to configure the required plugins on both Maven and Gradle, add the required dependency, and configure Spring Boot to be able to generate container images that will contain a native executable. You can also see that there is a generated help.md file that will provide you some getting started instruction to compile your native application and also some links to the documentation. Speaking about the documentation, Spring Native provides a complete reference documentation. The most interesting sections are getting started, because that explain really how you should start, and the support section that will list all the supported dependencies which are known to be supported on native. There are two main ways of building a native executable with Spring Native. The first one is based on build packs. Build packs, or cloud native build packs, are already supported in Spring Boot. That's how you can build containers, images with your Spring Boot application and the GVM. And what we have done is that we have added native support to build packs in order to create container images that contain a native executable created from your Spring Boot applications. It does not require any GraalVM native image compiler installed locally. Only Docker is required, and the build will happen inside the container and will produce a Linux-based container image. x86 is supported, and ARM support is a work in progress. You can follow this issue for more information. But that's more for deployment. If you want to work more as a developer, you will likely use native build tools. Native build tools started as a collaboration between Spring and GraalVM teams, and recently the Micronaut team have joined us. It's Maven and Gradle plugins that allow to compile your application using a locally installed native image compiler, and also it provides native testing support, which is super important. It produces a native executable of the same architecture of your OS. So if you are on Linux, it will produce a Linux executable, same for macOS and Windows. No cross-compilation is supported, but if you need cross-compilation, build pack support and the future ARM support may be an answer to that question. Now let's see concretely how to use that. With Gradle, for example, you type Gradle boot build image will be build packs, or Gradle native build with native build tools. And this will build a native version of your Spring Boot applications. If you have configured correctly Spring Native, that will work out of the box if you are using the supported dependencies. You can see that the native image compiler is run on both sides, but at the right, it's running directly on your OS, and at the left, it's running inside a container. The native build takes some time. Like I said, it's a small application, and you saw it took a few seconds. At the right, with native build tools, and a native executable is just created on your machine. And at the left, with build packs, a container image is deployed locally, and then you can run both. So while compilation takes time, startup is almost instant. So at the right, with native build tools, we are just running the native executable. And at the left, with build packs, we are using Docker run with the name of the produced container image to run it. And you can see that startup is almost instant. Here, we are starting this Spring application in less than 8 milliseconds. And even with bigger application, the startup is not more than a few milliseconds, so that really scale with your application. It's not just a demo. For the supported language, we support both Java and Kotlin. For Kotlin, you should use Kotlin 1.5 or superior. And this is the current scope of the Spring support that we provide. So this is the list basically of the actuators that we support. So we support Spring Boot actuators. Various Spring Data modules are supported: Elasticsearch, JDBC, GPA, Neo4j, R2TBC, and Redis. And we have support for various other parts of the Spring ecosystem, like AirSocket, Spring Security. Both Webflux and Spring MVC are supported. There is a support for testing. We are going to see that more in detail. Various Spring Cloud projects are supported. Logback is supported with some limitation. And we have Wavefront supported as well. Obviously, this list of dependency will increase over time, and that's just the beginning of the story. Now, I said previously that there is some native configuration to make GraalVM native image compiler aware of reflection, resources, and proxies. This is how it looks like. You have this reflect-config.json placed in a predefined directory on your class path, and native image will automatically read that to know that, for example, this class or this field or this method or this constructor need to be accessed effectively, and for resources and proxies, that basically is the same. But that's not super nice to write. That's why Spring Native is generating that automatically for the dependencies that we support. Now, what should you do when you are using a dependency from your company or a dependency which is not yet supported? You can write this kind of file if you want, but we also provide a more convenient way to add native support for your libraries if needed. If you are using some feature that require explicit configuration, it's those native ints annotations. So basically, you are using those annotations on your Spring Boot application or configuration, and that will allow you to specify that you want to add a specific native image command line runner option. You can specify with @typeInt reflection or access to class resources when that's required when you are using ASM, for example. You can specify additional resources. Out of the box, we are adding everything that is in SRC main resources and SRC test resources. But if you have a resource, for example, in one of your dependencies and that's not supported yet, you can specify that with that kind of annotation. And same for JDK proxy on interfaces, serialization. And with GraalVM, you have also the possibility to initialize some classes at build time. So we provide some annotation to specify that, but be careful about that. It can quickly become a compatibility nightmare. So please use build time initialization, not frequently. So let's now talk about the recent enhancement we did. The first one, and a very important one, is native testing support. So thanks to the collaboration with the GraalVM team on native build tools, we are now able to provide Gradle and Maven support for native testing. So concretely, that's based on JUnit 5, and with Sam Brennan, who is a Spring Framework and JUnit contributor, we are currently backporting and contributing some of those features directly in JUnit 5.8. The goal is to be able to compile your JUnit 5 tests as a native executable, and then the JUnit launcher is directly run from this launcher, and that will generate the regular report test file that will print the output of the test. And with that, you are able to test your application, including with integration tests on native. And also, that's a game changer for library authors who want to provide native support, and that allows them to test their library. Some features are not supported. For example, Mockito, which is heavily based on bytecode generation at runtime, is not supported, but we are currently discussing that with the GraalVM team, and there is some plan to fix that. But for now, yeah, Mockito and similar stuff are not supported yet. Another feature that we wanted to provide, because like I said at the beginning, we want to limit as much as possible the amount of modification to run your Spring Boot application on native. Typically, when we are using proxies on interfaces, those are JDK dynamic proxies that's supported by GraalVM native image. We just have to provide configuration for that, and that works. But what about proxies on classes? For example, see this example of Spring Security with a notation like pre-authorize on a class, or if you are using @transactional annotation on a class. It's not supported by design by the GraalVM native image compiler. So Andy Clement implemented AOT ahead of time proxy generation. So instead of creating this proxy at runtime, like we will do it with cglib on regular JVM runtime, we are going to modify the bytecode at build time in order to create this proxy. And then this kind of use case is supported out of the box. You don't have to modify your application. It should be detected automatically, but if we miss something, you can totally use @AOT proxy int to specify that. A new feature that we provide in the upcoming 10.11 release is buildpack support for compression. So buildpack now supports UPX compression, which allows to reduce the size of the native executable by a factor of 4. And compression takes some time, but native image build already takes a long time, so I'm not sure that's a big deal. And more surprising, at runtime, the startup is usually faster with the compressed version because decompression is more than compensated by less I/O. So for now, in the upcoming release, you will just have to enable a flag, BP binary compression method, in order to trigger this new feature. And we are going to see concrete figures about the impact of this compression support. Now, let's talk about ahead of time transformation. And I think this is the most important topic we are going to talk about today. So Spring AOT and Maven Gradle plugins perform powerful build time transformation on Spring Boot application to improve the efficiency on native and potentially on the GVM too. That's very important because we started this Spring native journey by adding hints in order to allow Spring Boot application run in order to specify the reflection, the proxies, etc. But nowadays we try to go one step further and modify at build times Spring Boot applications in order to run not natively on native because it will still require some configuration, but run on native with less configuration, better compatibility with native, and lower footprint. So here is a diagram that explains how you could compile a Spring Boot application to native with our new infrastructure and how that works. So as usual, you have your Spring Boot application sources, and you are going to compile it to application bytecode thanks to Java-C. Usually that's done via the Maven or Gradle plugins. But here, instead of directly passing that to native image compiler, we are going to invoke the Spring AOT plugin. So Spring AOT plugin is a plugin that is applying in parallel of the current Spring Boot one, and it's going to generate sources ahead of time. And it's going to generate those sources based on various on knowledge of your application. So you see that it takes in input the application bytecode, for example. Then these AOT sources are compiled with Java-C. So we have a two-step compilation. And the output is an AOT bytecode with the linked sources and the native configuration. And those three elements, application bytecode, AOT bytecode, and native configuration, are feeding the native image compiler in order to generate this native executable. The work that we did during the summer, and we, especially Stefan, Nicole, and Brian Kozel, who did an amazing work during this summer, is to process Spring application context bins at build time. We are not going to start the application context at build time because that makes no sense, but we are going to create it, analyze it, and generate a modified version that will be more efficient. So really big congrats to Stefan and Brian for this work. And let's have a deeper look on the architecture of this supercharged Spring AOT plugin. So if we go more in detail, in input, you have the application bytecode. We have talked about that previously. You have the class path, so typically the dependencies that your project are using. And here, Spring Boot had already, it basically introduced a closed world assumption for the GVM ecosystem used in a wide manner. And native image is doing the same, but in native image, it's mandatory. Everything in terms of dependencies is fixed at build time. So we can take advantage of that knowledge to provide additional optimization. In input, we have also Spring factories. So Spring factories are basically Spring plugin mechanism. It's similar to service loader, but with some Spring related features. And we are going to use that in input. Also, we are going to use your application properties like application.properties or application.yaml in order to understand the configuration of your application, at least the one that we can analyze at build time, because you can still provide additional configuration at runtime. Then we have the Spring AOT plugin, but the new version that will be available in our upcoming .11 version. We begin by doing an IoT application context processing. So the context is created with the various beans, but not started. We perform add conditional filtering. So add conditional, we are going to see that more in detail with the sample. Add conditional is the mechanism that allows Spring Boot to know what part of the configuration is required for your application and what part of those configuration are not required. And this process is typically done at runtime in a very efficient manner. But here we are going one step further because we do it during the build. And the output of that will be an optimized source code generated for your application and an optimized native configuration that will be generated based on the knowledge of the class path, of the various configuration of your application. And also it will use the native int that you could provide on your application and also the ones that we are shipping out of the box with Spring Native. We then compile those generate source code with Javac, and also we are doing this IoT proxy generation at build time. The output of what the plugin is generating are the programmatic Spring factories, the programmatic application context, the bytecode with IoT proxies, and the native configuration. We are now going to compare a regular Spring Boot runtime, like you do it today, to the Spring Boot runtime in IoT mode. So let's talk about how things works currently. So you have your Spring application. You are going to, in your main, you type spring application.run, for example. And what happens at runtime is that the Spring Factories file is read. So you have a Spring Factories example at the left, where you can see that for a specific interface, we provide various implementation. That's the plugin system behind Spring. And those Spring Factories files are provided with Spring Boot dependencies or via third-party libraries sometimes. This is obviously done by reflection because this file is like a property file. And also there is filtering of the configuration classes that is done via ASM class reading. So at the right, you have an example of one Spring Boot auto configuration, but you have, this one is specific to JSONB, but you have a lot of others. And have a look to this add conditional on class, add conditional on resources, add conditional on missing bin annotations. Those are the information that allows Spring Boot to know if this auto configuration should be taken in account for this application or not. We have done a lot of optimization in Spring Boot to make that super fast at runtime, but that still happens at runtime in this mode. So a quick filtering is done via ISM, and then for the retained candidates, Spring Boot is using reflection to load the configuration classes and create the relevant bins. Also, CGlib is used to generate proxies when required, like I showed previously. Now, let's have a look how that works when you are using the Spring IoT plugin before. Here, your Spring application is going to use directly the programmatic Spring factories that you can see at the left. Two main differences. The first one is that very few or no reflection is involved, because that's directly using functional constructs like lambdas and method references. So that's a good fit for native, because native could understand automatically out of the box without any native configuration this kind of construct. So better compatibility and also smaller footprint, because no reflection means lower footprint. And the other point, but the very important point, is that this programmatic Spring factories is really customized for your application. It only contains the bits related to your application. Then at the right, you can see that we have this programmatic application context sample. So instead of analyzing the various configurations, etc., we are going to bootstrap the Spring application context using lambdas and method references. So same than for programmatic Spring factories, the fact that we are using functional construct for creating the application context it's going to give out of the box a native compatibility, no reflection involved. And also we have done a lot of pre-processing because we have processed the add conditional Spring Boot annotation at build time, at least most of them. And so it's expected to be faster. No need for reading the class resources. If we need to do that with the ASM, we can do that at build time. And also no bytecode generation, since that's not supported by native, but that also happened on the GVM. Is directly used the AOT generated bytecode with required proxies. So to summarize our Spring ahead of time strategy, move most configuration reflection from on time to build time. It's not about removing reflection, because reflection is needed when you are using annotation-based powering model. It's more about moving reflection from runtime to build time when that's possible. We don't need to remove totally reflection because a lot of libraries are using reflection. And I think it's totally enough for Spring to, for itself, move all or most reflection at build time, and then just use what the GVM ecosystem is using, and not try to do that work instead the ecosystem. It also allows to reduce the amount of Spring infrastructure required at runtime, because with this AOT mode, we are just using a very simple generic application context variant. We don't need all the annotation processing, etc. So that's nice, because we are using less class from Spring at runtime. Maven and Gradle plugins are doing source generation. That's super important for us because we want to keep good debuggability. So we are generating the sources, and we are generating the bytecode. We are compiling those sources to have both sources and bytecode, including for the generated bits. We have explored annotation post-processors, but they were by design too limited for our needs, so that's why we are not using them. And so at runtime, AOT mode is mandatory on native, because we are really using that to provide our native support, to reduce the amount of native configuration. And it is optional on the GVM. Currently, it is enabled when you are using the AOT plugin during the build. And then at runtime, when you are using the -d Spring AOT equals true flag to enable that. So let's now see data points, because I think that's super important. Let's begin by the native drawback, the long build time. So in those figures, I'm going to compare command line runner, which is a Spring Boot sample, which just prints something on the command line. WebMVC Tomcat, it's a Spring MVC application, a Spring Boot plus Spring MVC plus Tomcat application with an at-rest controller endpoint. And Pet Clinic JDBC, which is the JDBC variant of our famous Pet Clinic sample. So closer to a real-world application. On the GVM, compilation takes a few seconds, as usual. On native, you see that it takes here between 1 and 3 minutes, because native compilation takes more time. But you can see that between the currently released Spring Native .10 version and the upcoming Spring Native .11 version, we have done some progress, because when we remove reflection and when we do more optimization, for example, better Java 11 support or things like that, we are reducing the build time. So really, the way to reduce the build time is to provide less bytecode to compile to the native image compiler, and the GraalVM team is doing some optimization, and on Spring side, we are doing some optimization as well. Next, let's have a look to the container image size, even if that's not the most important metric. On GVM side, if you are building a container image with Spring Boot build image, it will ship a GVM version in your container and the bytecode and the dependencies. And so you can see the size of the container image is around 200 megabytes with the GVM. Be aware that we are working on some optimization to use a thinner operating system layer to reduce this amount, but currently this is what you have. And then with Spring Native, you can see that we have smaller container images because we are using a very teeny operating system base layer, and we are just shipping the native executable. No need to ship the whole GVM, and no need to ship the dependencies, etc. And last point, with UPX compression, you can see that we have very small containers. So for example, for the pet clinic application, we have a container image that is less than 50 megabytes. That includes the operating system and the Java, Spring, and your application bits compiled into a native executable. So I think that's a pretty nice figure. If we do a deep dive into a minimal native container image, you can see that you have a base layer for the operating system, which is only 17 megabytes. Yeah. It's containing glibc, it's containing OpenSSL and a few other libraries, but just that. And here you have Spring Boot plus Spring MVC and Tomcat application compressed via UPX and built with native image compiler. And you can see that it's only 15 megabytes, so pretty small and optimized. Now, probably the most interesting point, the memory footprint. So here I compare various flavors of our Spring Boot applications. For the GVM, I'm just running, so this is a benchmark on Mac because a result can vary a lot between platforms, but here that's on Mac. So if you run your Spring Boot application following the guidelines of deployment, so it's an exploded Spring Boot application, you are going to have these figures. So for example, for Pet Clinic, you have 245 megabytes of memory consumption, and this is the RSS memory. So this is the total amount of memory, not just the heap, the total amount of memory consumed by the related Java thread on your operating system. Now, it's interesting that even without compiling to native, just with the GVM, with the AOT mode on the GVM, we observe a significant decrease of at least 10% of memory consumption for the very same application. So that's interesting because we have not yet begun to work on GVM specific optimization. It's just the AOT mode that we have built for native, and it provides some interesting improvement in terms of memory footprint on the GVM. Then on the native side, you can see that we have a pretty low footprint. And you can see that we did pretty nice improvements between our current release and the upcoming one. And we will continue to do that. Those improvements are due to two things. The first one is the better Java 11 support. We have been collaborating with the GraalVM team because Java 11 native images were bigger than Java 8. So we had a great collaboration on that, and thanks to them for fixing that. And also, this is the outcome of the new AOT mode, which is more efficient, basically. And those results are likely to be even better in our upcoming release because we are going to leverage GraalVM 21.3, which provides some pretty significant optimization and reflection. More on that later. Startup time, here, I guess that's a no-brainer. Native is the winner. But again, you can see that on the GVM with this new AOT mode, we observe a 10% minimum gain in terms of startup time on the regular GVM. So if you combine that with other GVM improvements, I think that could be an interesting point to explore. And on native, the new AOT mode with the application context created and analyzed at build time allow faster builds, but yeah, it's faster, but it's still a few milliseconds. But that's always nice to be able to start even faster, especially for bigger application with a lot of configuration. I think that will be even more interesting. Now let's talk about GraalVM 21.3. GraalVM 21.3 will be released in October, and it provides major improvements to reflection supports. It also introduces the Java 17 support, which is super interesting because that's the new LTS version. and it will remove the Java 8 support. So don't be afraid, you can still compile your Java 8 application using the Java 11 distribution of native image, for example. But I think that was really needed to remove the Java 8 support because native was super difficult to maintain for the GraalVM team on this platform. And it's important to be able to move forward because in more recent version of Java, there is some native related improvements that make it much easier to support native. Our coming .11 release will be based on GraalVM 21.3. Current snapshots are still based on GraalVM 21.2, and will provide both Java 11 and 17 support. Let's now talk about the improvements in terms of reflection. So a new feature of GraalVM 21.3 will be to distinguish between invoked and queried reflection method to allow better efficiency. Because currently, when you configure reflection on GraalVM, it's going to provide the reflection metadata like annotations, and also create some proxies to allow invoking reflectively methods or constructor. And there was no possibility to differentiate those two use cases. And by allowing to do that, the GraalVM team was about to measure up to 20% footprint reduction with Spring applications. So we are excited to be able to leverage this new feature. Reachability-based native configuration is also super important. It's allowed to reduce the amount of build time class initialization, which was previously the main way to reduce the native image size. But that's a dead end in terms of compatibility from my point of view, and I think most of the GraalVM team share that. So this proposal is about adding a when type reachable predicate that allow you to make a reflection entry of the GraalVM native image configuration only active when a certain type is reached by the native image static analysis. And that's super powerful because that allow you with a static configuration to take advantage of this static analysis. And that should allow to switch everything to runtime initialization with low footprint and avoid the issue, or begin to avoid the issue of build time class initialization. So that's super promising for the compatibility and the footprint of native libraries. Last point, for simpler reflection calls that where arguments are constant, those simpler calls will be automatically inline. That means no extra memory is needed for reflection, and no configuration is required for those reflection calls because they are directly inline during the build. So I think that's pretty promising. That does not work where the arguments are dynamic, so it has some limitation. But for some use cases, that enables some interesting improvements in terms of compatibility and footprint. Now, let's finish with the roadmap. So our next release will be Spring Native .11. The key features are this IoT application context, the GraalVM 21.3 with reflection optimization, Java 11 and 17 support. It will be based on Spring Boot 2.6, and it will provide UPX compression for container images. Milestone will be published shortly, and it will be released the same time than Spring Boot 2.6 during November. Now, a very interesting point, VMware Tanzu adds end-to-end native support. So VMware and Bellsoft now have a support agreement in place that provides end-to-end native support to VMware Tanzu customers via Liberica Native Image Kit. Liberica Native Image Kit is a native image distribution maintained and created by Bellsoft, and it is based on the GraalVM Community Edition and Liberica JDK, and it will be used in native build packs as of Spring Native .11. On the user side, no change. You are still using the same native image command, but that allows us to provide native support end-to-end. And that's consistent with JVM side because there, the Bellsoft Liberica JDK was already used. So that provides a consistent story on both JVM and native. And fixes and enhancements will be contributed upstream to the GraalVM project. We continue to have a great collaboration with the GraalVM team, and that will allow us with Belsoft to contribute more to the low-level stack of native image. As announced by Jürgen during the keynote, the future of Spring Native is first-class native support in Spring Boot 3.x. So I think this is the most important point. Spring Native will remain beta and will get merged gradually in the next generation that we are starting to build right now. More detail about that. First, I had previously hinted that will happen, but now we have a clear roadmap with some dates. So Spring Framework 6 Milestone 1 will be available Q4 this year. The RC1 will be available Q3 next year, and the GA will be available Q4 next year, with Spring Boot 3.0 GA following after that. And don't be afraid, we will provide a smooth migration path from Spring Native, from using Spring Boot with Spring Native to Spring Native 3, which will provide out-of-the-box native support. And I share with you here a small, detailed architecture that will likely change as we implement it. But basically, on GraalVM side, we are going to continue contributing on native build tools for the Maven and Gradle plugins. We are going to introduce and work with the GraalVM team on a native configuration repository for libraries, and that will use the GraalVM 21, the next release of GraalVM, the 22.x. Paketo build packs will continue to mature native build packs, and the Spring Boot 3 is where the native support will really comes with AOT support in Maven and Gradle plugins. Spring Framework 6 will provide the basis for the AOT transformation engine and native foundational support and key enablers. And each Spring portfolio project will provide AOT transformations and minimal native ints if needed. The goals are really seamless integration in Spring Boot, increased native support, so supporting more libraries, also better quality because there will be much more testing and not just integration testing. Runtime efficiency via AOT transformation for both native and JVM. So even if you stick to JVM, I think that's interesting. And a Java 17 baseline because it's better to leverage the latest Java version for that. Again, this Java 17 baseline will allow to compile most of the previous version of Java. So if your project are using Java 8 or Java 11, most of them will compile, but we want to leverage all the new features that provided by Java 17 and be able to evolve faster, but not maintaining too much Java version support for native. The collaboration with GraalVM team continue to increase. And I'm sharing again this quote by Thomas Woslinger. And I'm super happy about the work we do with the GraalVM team, with Thomas' team, and big thanks to Vojin Vojinovic. We are collaborating. We have a great collaboration with his team, and we will continue to collaborate with them. An example of this native configuration is the upcoming native configuration repository. So native configuration for JVM libraries, the goal remains direct inclusion in those libraries, and the testing capabilities will help. But for the libraries that are not yet ready to include the native configuration, we are going to collaborate with the GraalVM team on a native configuration repository that will allow to provide native configuration for a specific library if it does not provide native support yet. All non-Spring native ints will be moved to this repository and will be directly used by Spring Boot 3. And we will provide guidelines on how to craft native configuration, how to test that, and some advice about some best practices, basically. There will be an automated testing of those support in order to be able to test when a new version of a library is released, if the native configuration is still relevant or not. So in summary, we are really building a framework for the next decade, and that's why we are working on those stuff. The Spring team is fully committed to build a strong Java native ecosystem, and you can use Spring Native today to compile your Spring Boot application to native executable. And then when Spring Boot 3 will be released with this IoT optimization and native support, it will benefit to millions of Spring Boot applications, and you will be able to leverage that with better compatibility, even more optimized footprint, and full support on that. Okay, I would like to say thank you, and you can contact me at sdollars on Twitter if you have some questions. And I think we are going to share the Q&A session link on Slack, and then you could ask me questions.
Awesome. I hope you all really enjoyed Sebastian's session. It was packed with so much detail, from a recap on native to recent announcements, performance statistics, GraalVM, and a future roadmap. I'm not sure what was it that he did not speak about. If you have questions for Sebastian, he'll be available on Zoom right now, and you'll find a link to that Zoom on your Slack. The Q&A will also continue on Slack for some more time, so make sure you catch both of those things. Next up, yesterday, if you saw our RSocket keynote, you'll remember that we showed you all of those RSocket frames which are passing through Canva. Canva, if you're not aware, is a $15 billion company that builds a visual design app that is collaborative. And that app uses RSocket. Let's hear from Sergey Selovanikov from Canva on how to create a collaborative applications at scale using RSocket.